Hello and welcome. My name is Mr. Wagner. This is your Algebra 2 class, and today we are learning about imaginary numbers. Let's begin. This is section 5.4, imaginary numbers. Today we will be able to understand and perform operations on imaginary numbers. For some reason, skipped all the way back. There we go. We're going to solve this problem using the square root method. It's kind of an introduction. This is what we did the last video. Let me bring up my pen. Basically, if we want to use the square root method, our objective is to isolate the x squared term. We're going to do that by dividing both sides by 4. We're going to get the value of x squared equals 25. Once you're here, square root both sides. Make sure you throw the plus and minus on that. And you get a nice whole number because 25 is a perfect square. Actually, x is plus or minus 5. Because when you plug in 5 into here, your output will be 100. Boom. This is what we did in our last video. We solved quadratics using the square root method. We're going to be doing the same exact thing today with one little imaginary twist. We are now going to solve the same problem as if though it was a negative 4 in front instead of a positive 4. So when you're here, we're still going to perform the same exact steps. We're going to divide. We need to isolate our x squared term. Oh, of course, we have technical difficulties. This will happen every video from here on out. So please bear with me. No. Okay. Just please fast forward until you start to see pens being drawn. I promise you, when I'm in the classroom, I don't make these problems this dramatic. I just solve. Please make sure to skip forward until you see pens being written. No one should be listening to this right now. There we go. Boom. Okay. We begin. When you divide both sides by negative 4, you'll notice your right-hand side gets you negative 25. At this point, you should be feeling a little uneasy because we should know as math students at this point, if you're squaring a number, what's the possibility that it can equal a negative value? Right? I want you guys to have a calculator. If not, if you don't have one on you, we bring up the decimals calculator, the scientific calculator that's on our front page. I want you to attempt to try to type in your calculator square root of negative 25 and see what happens. For those of you, let's go ahead and try that myself. Go here, online calculator. I'm going to try the square root of negative 25. Equals right here. Your answers show up right here. It says this word undefined. Normally, your calculator will blow up in small smithereens. This is what happens when you type in the negative numbers in your square root. On Desmos, I will show you what it looks like graphically. Right? If I were to show you when 4x squared equals 100, you'll notice we do get two answers when it's just 4x squared. You get plus or minus 5. However, if I were to type this in negative 4, notice my quadratic is now concave down. It comes nowhere near this output of 100. Does not intersect it. This is what it looks like graphically. It just doesn't intersect your y equals 100. It means it will never be equal to 100. And that's because it's always going to be negative. You have one brief point where it's 0 at your vertex, and from every point on, this thing just goes more and more negative because this is a concave down parabola. It will never have any positive outputs. The reason why this happens is because when two numbers are multiplied by each other, it's impossible for it to equal a negative number, as long as it's the same exact value. This is undefined. The issue does not compute. What we call this, normally up to today, we just said no solution, which for real values is 100% accurate. Today we're going to learn about these things called imaginary solutions. Not that they have to think them up yourself, but basically numbers that don't technically exist, but we can use kind of like a placeholder to bring back to life. Let's see. This will, all right, we're going to the next page. Once again, square root of negative 25, this would be undefined. Next page. When you're square rooting a negative number, it turns into an imaginary solution. We found ways to kind of describe this by this right here. We call the square root of any negative number, square root of negative 1, sorry. We call the square root of negative 1 an imaginary number because it does not actually compute. There's no way you can multiply two numbers together to get negative 1. My pen is currently not working again. Just new batteries right after this video. All this means is when we're computing, we're using square root method to solve quadratic equations. If you get to the point where you're going to be square rooting a negative number, we're going to start using I. We're going to use imaginary units in order to represent that answer. So let's show what it's going to look like. This, for example, if I want to represent the square root of negative 5 in terms of I, we always want to take my negative 1 and kind of factor it out. So underneath your square root, you'll notice I could rewrite negative 5 as 5 times negative 1. The square root of 5, I could write just as that. That's a real number. It's irrational. Right? We can't take the perfect square of 5, but we can write it just like that. You break it off into two separate square roots. Right? Once you have that square root of negative 1 on the right-hand side, we're just going to replace it with its variable that's equivalent to, which is I, which we define as a square root of negative 1. We're left with square root of 5 times I, which can be written just like this. Just make sure. When you write out your I, it's outside of your square root symbol. Because we're already taking the square root of negative 1, do not write your square root symbol over I. I'll show you what I mean. Next one. Right here, square root is negative 16. Rewrite as root 16 times the square root of negative 1. Root 16 has a nice number. It has a perfect square. It's just 4. Square root of negative 1, we label it as I. Just like that. 4I is the same thing as square root of negative 16. Last one, square root of negative 18. Break off into its two parts. Square root of 18 times square root of negative 1. Square root of negative 1, once again, is I. Square root of 18, we could break down actually into 9 times 2. Reason why I did that is because 9 has a perfect square, or 9 is a perfect square, which means I'm going to rewrite the square root of 9 times 2, equivalent to 3 root 2 times I. Notice here's my whole number coefficient, 3, my radical term, square root of 2, my imaginary number, I. Do not, once again, this radical symbol right here, do not put over the I. Leave it as is. The I lives by itself. I is independent of its radical because it's already represented as such in its definition. That's how you write solutions. Here's your property right down here. If r is a positive real number, then the square root of negative r, all you do is pull out that imaginary number and throw it out front. Let's go here. We've been solving things the same exact way. Via square root method, we're still going to solve these just the way we did. Just we're going to have imaginary answers. When you square root both sides, you get your plus or minus square root of -5. We don't like leaving things with square roots of -5 underneath it. So what you're going to write is square root of 5 times square root of -1. So when you see that, whenever you see square root of -1, just replace it as I. You will get to the point where you can skip this middle step without breaking it down into 2 different components. Just write tag I on the end of it. But I will be solving it like this for this whole day today. Number 2, once again, to isolate your x, square root both sides. You get x is equal to both the positive and negative version of the square root of -4. We don't like square root of -4, so we leave it as square root of 4 times square root of -1. We can take the square root of 4, these will be plus or minus 2, and then your square root of -1 becomes an I, just like that. Number 3, isolate your x squared term before you square root both sides. 3x squared equals -36. X squared is equal to -12. Anytime you have a square term on the left and a negative number on the right, you will have imaginary solutions. As long as your x squared is isolated. This gives you plus or minus square root of -12. This is going to be a double one because 12 does have a perfect square factor. This becomes square root of 12 times square root of -1, which is equivalent to 4 times 3 times square root of -1. When you see that your number has a square root or a perfect square factor, please always make sure to take it out. Square root of 4 is 2, so pull out that 2. The square root of 3 still lives underneath that symbol, the radical symbol. This turns into an I. Boom. Plus or minus 2 root 3I. So there's a lot of steps with reducing radicals. Just make sure anytime you have a negative number you're square rooting both sides of, just replace that negative number with your solution with tagging I at the very end. And your I always sticks in the back, always in the caboose. The last thing you write for your answer. So complex numbers in standard form written as a plus bi, where a and b are real numbers, refer to you're adding imaginary numbers with your whole numbers or integers or real numbers. We always write in the form of a plus b times I, where this is a real number that goes in front. This is your imaginary number. You're either adding or subtracting in the back. Always make sure your imaginary number is the last written and your I term is behind that coefficient. The best part about these operations with complex numbers, we treat them just like any other variable. Treat I just like any other variable. When adding and subtracting. There's one difference when multiplying, we'll get there. But when adding and subtracting, treat treat it like any other variable. So if I told you 4 minus I, this is my complex number, plus 3 plus 2I, we're going to combine the constants. 4 plus 3 gives me 7. Negative I plus 2I gives me 1I. 7 plus I is how you reduce part A. Combine your like terms. That's all we're doing. I's add and subtract just like any other variable. Part B, 7 minus 5I minus 1 minus 5I. Make sure if you have a minus in a term with parentheses right behind it, you're basically distributing that negative sign to both terms. Would rewrite this by getting rid of those parentheses. You're subtracting 1, you're subtracting negative 5I, which turns into positive 5I. Make sure that positive 5I comes back to that very last one because we're subtracting a negative term. The double negative turns into a positive. From here, 7 minus 1 gives me 6. Minus 5I plus 5I turns into 0. This just leaves me with 6. So you can have two complex numbers, perform operations with, and result in a real number. Last example, 6. You see this minus sign, make sure to distribute that minus sign to everything inside those parentheses. You are subtracting a negative 2, which means you're adding 2. You are subtracting a positive 9I, which means you're subtracting it. This plus symbol just means we're going to rewrite it as is. Using my terms, combine like terms, 6 plus 2 minus 8. Combine your whole numbers. 6 plus 2 minus 8 gives me 0. Negative 9I plus 4I leaves me with minus 5I. That's my solution because my constants cancel out. So once again, when adding and subtracting complex numbers, treat the constants and the i's, imaginary numbers, separately, and they combine just like any other variable would. Now we're going to compute multiplication of complex numbers using the distributive property. So once again, just like we have in the past, we're going to distribute like any other normal variable would. I'm going to get into simplifying some of these on the next slide, but for now, we're going to simplify everything we've known how to do up to this point. 5I times negative 2 gives me negative 10I. 5I times I gives me 5I squared. Now there will be, I'm going to show you guys the next page. There's a way to reduce, and anytime you have an I to a different degree of 1, those can be reduced. But for this page, I'm just going to simplify it until we get, for this page, I'm just going to simplify it for what we've been doing up into our mathematical careers. Here, part B, we're going to use distribution of two binomials. For those of you who call it FOIL, that's what we're doing. First is 7 times negative 1 gives me negative 7. Then 7 times positive 2I gives me 14I. Negative 4I times negative 1 gives me positive 4I. And negative 4I times positive 2I is minus 8I squared. Make sure if you're multiplying two i's together, you get I squared. Then once again, combine like terms. Negative 7 is the only term here. Positive 14, positive 4I gives me positive 18I minus 8I squared. This is really the only time we ever write down I squared as is, because I want you guys to kind of think about for now this little top right thing. If I is equal to square root of negative 1, what do we think I squared is? Think about that while I'm going to FOIL this last portion. 6 times 6 is 36. 6 times negative 3i is negative 18i. 3i times 6i is positive 18i. And 3i times negative 3i gives me negative 9i squared. Combined like terms, these two in the middle cancel out. We're left with 36 minus 9i squared. This begs the question, if I is equal to the square root of negative 1, what does I squared equal? If I took square root of negative 1 times the square root of negative 1, what would that give me? That next page. This is a huge property. I would try to write this down. When we're simplifying operations with complex numbers in which we're multiplying them, anytime you're squaring your I value, what happens is I squared turns into a real number. Two imaginary numbers squared, or when you multiply two imaginary numbers together, that square root cancels out and leaves you just with what's underneath the radical, in this case, negative 1. This is a great cheat sheet for what could help you out down the road. If you have an I value, it's equal to the square root of negative 1. If you multiply I by itself, so square root of negative 1 times square root of negative 1, the square roots cancel. You're left with I squared is equal to a real number. I squared is negative 1. You can turn imaginary numbers into real numbers using this. I cubed is equal to a negative square root of negative 1. I to the fourth is equal to positive 1. Notice why this happens is if you keep on multiplying, my pen will come back. If you continuously multiply by square root of negative 1, some kind of operations will slowly change from, they'll alternate between being imaginary and real and being positive and negative. Then notice I to the fifth is equal to the same thing as I. That's because we went back, we multiplied by it so many times, we reverted back to itself. I to the sixth is the same thing as I squared. Et cetera, et cetera. It follows this pattern. These four, it follows this pattern. I is equal to square root of negative 1. We squared it equals negative 1. We multiply it by I again, it becomes negative. And I to the fourth turns into a nice whole number of 1. So we will reduce using this understanding. Let's do that right here. 7 times negative 6 gives me positive 42. Negative 7 times negative 3i, this becomes positive. 7 times 3 is 21. Tag on your I value. Negative 6i minus 6, when you multiply these out, it becomes positive 36i. Lastly, minus 6i times minus 3i becomes positive. 6 times 3 is 18, and I times I is I squared. Combine like terms, your 42 stays as is. 21 plus 36 gives me 57i. When you see this, you have to simplify every I squared term. We know that I squared is equal to negative 1. Knowing, understanding this, rewrite it as such. Plus 18 times negative 1. Which notice, like I said, when you square I, it becomes a real number. 42 plus 57i, 18 times negative 1 is negative 18. All of a sudden, we can combine these like terms. 42 minus 18, 42 minus 10 is 32, minus 8 more, 24 plus 57i. There's a 57i coming. Oh, no, went back in time. There we go. Nope. 24 plus 57i. going to do one more example after this. I don't know when. I'm going to do one more example after I can write down 57i. Here we go, 57i. 24 plus 57i. Boom. Well, it says that's the end of it. Keep this. I'm going to do one more example on my OneNote real fast, just so we get a great baseline of understanding this material. But if I were to take this pen's not working again. There we go. For example, if I had 3 plus 4i and I multiply it by 3 minus 4i, this is a good trick to show, because notice these are very similar, and something special will happen when you multiply these two out. So 3 times 3 gives me 9. 3 times negative 4i gives me minus 12i. Positive 4i times 3 gives me positive 12i. Lastly, positive 4i minus 4i gives me minus 16i squared. Always make sure you multiply 2 i's, it gets I squared. These two middle terms cancel out. We're left with 9 and minus 16i squared. We're going to rewrite I squared. It's negative 1. That's exactly what it's equal to. Negative 16 times negative 1 becomes positive 16. This is equal to 25. Ding, ding, ding. So this is kind of important in general. When we're multiplying imaginary numbers, just understand this is what happens. This is why we use imaginary numbers. When you multiply two imaginary solutions together, you will get a positive answer. That's kind of, like I said, we use them as a placeholder in mathematics to kind of generate those answers. Thank you, and have a great day.